Welcome everyone to the first video in the series. Today we're going to be discussing equilibrium. And so what we're going to see in equilibrium is that reactions don't just go to completion. You know, we may have sort of looked at an A to B look at chemical reactions when we were first getting started in chemistry. But in reality, we're going to end up having some portion of A and some portion of B existing in equilibrium in many cases. And this is not to say they're in equal amounts. The amount of A and B that are present is going to be different for every different reaction. How we study that is key to equilibrium. And I would also add that equilibrium is really the central topic that ties together everything in Chem 2. So whether it's just equilibrium of a general type of reaction, or if it's acid-base equilibrium or solubility equilibrium, it will come up over and over and over again, and developing as strong of an understanding as you can now really will help. And so with that, we'll go ahead and jump into the video. Welcome to our first video in this OER for Chem 2 series. The first thing we're going to be talking about is chemical equilibrium. And this is a really essential topic because it totally is the backdrop for all the chemical phenomenon that we're going to discuss here in Chem 2. Whether we're talking about solubility equilibrium or acid-base equilibrium, the fundamental principles of reactions that do not always go to completion 100% is going to be what we're looking at. And this image here shows this quite well. We have a reaction between N2O4 and NO2, and what we see is that when we are at equilibrium, it's not like we've gone completely from reactants to products, which may be a way that we've thought of reactions previously. What we see is that we have a percentage of each that are present at equilibrium, and though we may start as all reactants, it will get to that state where there is a certain amount of reactants and products. This balance is going to be different for every reaction. It's not going to be 50-50, but what's key is that there is some balance between reactants and products that we need to mathematically be able to determine what this relationship between those is, and that it applies to many, many, many chemical systems. Okay, so how do we determine the concentrations of products and reactants at equilibrium? Because as I mentioned, this is going to be a different balance, a different ratio for every system that we're dealing with. And we do it with the general form shown here. We're going to call this the equilibrium constant K, and we're going to see that there's a lot of different types of K values that we're going to investigate in this course. And here we're going to call it Kc, which is to say the equilibrium constant based on molar concentration. And as such, we've put the reactants and products in square brackets, right, to indicate molarity, molar concentration. And if we have something that has a certain amount of A, so like lowercase a would be the coefficient, so it could be 2A, 4A, whatever, plus a certain amount of B goes to a certain amount of C plus a certain amount of D, we are going to say that this is products over reactants, right? So C raised to the C power times D raised to the D power. We want to make sure that we're getting those coefficients in the balanced chemical equation to be exponents in our K expression. Products over reactants, making sure to raise each of our species to that coefficient. So why don't you take a little practice here? Let's say that instead of this general form of equation, we have this specific equation. What is the equilibrium constant expression for this? And I would recommend you go ahead and pause here, try to write it down. We'll use it moving forward and see what you come up with. All right, hopefully you've written down what you think K is equal to here. Again, K is going to be a number for everything, but we don't always know what K is for the reaction, so being able to recover this general expression that K is going to be based on is very important. And for this reaction, K is going to be equal to HI squared over H2 times I2, right? We want to take that 2 coefficient in front of HI and make that an exponent. Okay, so what if we now know that at equilibrium, we're going to have certain conditions? Because K is going to describe the system at equilibrium, right? K says that K is some number, and K is going to describe this ratio of products to reactants. If K is really large, that means that the numerator of the expression on the right is going to be really large, right? We're going to have a lot of products. Lots of products means we're going to have a K that's very large. And it could be very, very large, right? It could be K equals 10 to the 20 or 10 to the 30. If we have a lot of reactants, it's going to be very small, right? Large denominator means a very small value of the expression, right? So if it's almost all reactants, we're going to see Ks that are like K equals 10 to the negative 10, negative 20, something like that. It really does span this entire range of numbers. So if we want to determine the equilibrium constant K here, what's very essential is that when we're reading this problem, it says that we are at equilibrium already, right? We have a 4-liter flask. This reaction is at equilibrium, and we have a certain amount of HI, a certain amount of H2, and a certain amount of I2. So with what's given to us in the problem, we have the system sort of known already, right? We know what the ratio between reactants and products should be. And so we want to first put these into molarities because that's what is determined here by K, right? If we have, 4 moles, 8 moles, or 12 moles, we don't want things to be calculated differently compared to if it's 0.4, 0.8, and 1.2 moles, right? It behaves based on concentration, right? Kind of the density of each of these particles that are present. And then once we do that, we see that it's 1 molar, 2 molar, and 3 molar for each of these species. We go ahead and plug into this K expression our numbers, and we can recover K. Now, this K value, 4.5, this is going to apply to every system that is at equilibrium. So if the system is at equilibrium for this particular reaction, it's going to have this K value that evaluates to 4.5. And we're going to see how we use this moving forward as well. Okay. Conceptually, when we think about equilibrium, it's important to know that equilibrium is not a static state, right? It's a dynamic system. And so let's take a look over here at this graph. This is the same N2O4 to 2NO2 that we've looked at previously. And we consider what happens over time, right? Initially, we have all N2O4, right? And over time, the NO2 increases while the N2O4 decreases until we reach some steady concentration and equilibrium is achieved. We don't know exactly what those are going to be without K, but we know that there are going to be some non-zero values for both of them. There will be some reactant and product at equilibrium. However, what's also important to know is that they're not just like stuck there and nothing is moving around, right? They are actually both turning from one end to the other at the same rate. And so we can look at the rate of this reaction, where in the blue line, this is the rate of the forward reaction, where what is the rate at which N2O4 is turning into NO2. And initially we see that it's all that, right? If we look at time equals 0, we see that the blue curve is positive at its peak, and therefore that's the maximum rate at which reactant is turning to product. Conversely, we see that the red line, the reverse reaction, is equal to 0. There is no product, and therefore there is no rate of that reverse reaction. But as we increase in concentration, we see that the rate of the forward reaction decreases as less N2O4 is present. And the rate of the reverse reaction will increase as we generate NO2 that will, to an extent, want to turn back to N2O4. And when we achieve equilibrium, what's occurred is that those two rates are the same. The rate at which the forward reaction is moving is the same at which the reverse reaction is moving, right? Imagine, you and a friend both are holding a rock and you're sort of passing the rocks back and forth. You're always going to be holding one rock, right? And this is the dynamic state of equilibrium. The fact that these rocks are exchanging hands and the fact that N2O4 and NO2 are continually shifting back and forth into one another at the same rate, so the concentrations are constant, this is an essential qualitative thing that must be understood about equilibrium, right? We call this dynamic equilibrium, even though the concentrations aren't changing and even though the chemical activity may not be able to be harnessed, there still is something that's going on at the state of equilibrium. Okay, so what about if we don't have equilibrium, right? What we can do is we can test for equilibrium with this value we call Q, right? So if the state may or may not be at equilibrium, we can check using not K, but we'll call it Q. And we do this in the exact same way as K, right? If we have A plus B goes to C, we say that Q is equal to an expression that's just like that K expression, right? C over A times B. And with this, what we're going to do is we're going to check with the values that we have how Q would compare to K, right? We don't want to call it K because K is very specifically to an equilibrium state, and Q may or may not be. So while this form is the same and we're going to be able to use it to compare, we don't want to use that same terminology, K, right? If we determine that the number that we calculate for Q is the same as the number for K, we're going to know the system is at equilibrium, right? Q equals K, then we may as well have used K and everything checks out, equilibrium. If Q is greater than K, this expression is too high, which means there's too many products. And what the reaction can do is it can move to the left, right? It can take some products, create reactants. This is how reactions address not being at equilibrium. They can move in one direction or the other. If Q is less than K, this shows that there's too many reactants. Denominator's too big, and the reactants are too plentiful. And therefore, we're going to shift to the right. So by calculating Q, we can see, well, what does the reaction need to do to get to equilibrium? Because equilibrium is the state at which reactions prefer to be. It is their lowest energy state, and it's what they're going to want to drift towards if left to themselves, which is to say no energy input and things like that. Okay, so we're going to work through this question together. I'm going to sort of put the steps that you're going to go through to solve, and I would recommend that as each step is revealed, you sort of pause and see if you can do each step. I'll try to go slowly, but do pause the video as we go along with this description, and if you want to just pause the video now and try to solve the whole thing, that would be a great thing to do. So perhaps go ahead and pause, read the question, and then if you need help, feel free to work along with my stepwise solution. Okay, so the question we have here, is this system at equilibrium, right? We have a 1 liter flask with a certain amount of each of these species. And so the first thing we're going to want to do, right, is we don't know if we're at equilibrium, so we want to set up a Q expression that looks just like K. So basically for this chemical reaction, we need a expression that we're going to use. It's K, it's Q, right? We form it the same way. And in this case, it's going to be the NOCl squared over the NO squared and the Cl2 not squared, raised to the first power, which is to take into account the coefficients of 2 in front of NO, 1 in front of Cl2, and 2 over on the product side. What's the next thing we do? Well, we want to plug in our concentrations and solve. And keep in mind here that the concentrations are all numerically equivalent to the number of moles that are there because we're in a 1 liter flask. But you definitely want to make sure that you're not just dropping mole values into these concentrations. We absolutely need to take into account the molarity of each of these species. But numerically it's sort of the same, so if you miss this step, you kind of got off the hook. But be aware of that need to put the units into molarity for sure. Now we calculate. We get a value of Q equals 6.45 times 10 to the 3. And K is already known from the expression itself. And this will often be the case, right? Oftentimes you have a reaction, you know the value of K because it's known for all different balances of how much you should have, right? It's an identity of the reaction. So oftentimes K will be known and you'll need to do some evaluation of your state using what you know about K. With this, we can say, well, what is the difference between Q and K? Well, it's not equal to K. Is it bigger? Is it smaller? And as it turns out, Q is less than K. 10 to the 3 is less than 10 to the 4, right? This is 6,450 versus 46,000. And therefore, we know that this reaction must shift to the right. Q is less than K, too many reactants, not enough products, same kind of thing. And therefore, we need to shift to the right. Okay, so the last thing I want to cover here is what's called Le Chatelier's principle, and this is something that we've kind of looked at in the previous slide as well, which is addressing how reactions shift to reestablish equilibrium. Here in the previous slide, right, we say, well, we have a certain balance where there's too many reactants. Q is less than K, therefore it's going to shift to the right. What Le Chatelier's principle says is that, let's say we have a system that is at equilibrium. And a lot of systems we know there's no chemical activity going on, it's initially at equilibrium, and we can do kind of a qualitative look at what things are going to occur if we are to change the chemical system that's at equilibrium. It will want to reestablish equilibrium. And this is to say that a shift we can do, a stress we can put on the system is let's drop some reactant in, either A or B. What happens then is now we have too much reactant, right? It's at equilibrium, but we introduce some new reactant, which could be A or B. We don't have to introduce both. It's going to shift to the right because it needs to take that too much reactant and make some of it into product. If we add too much product, it's going to need to become reactant because the balance is going to be too far to the product side, and it's going to shift to the left, right? Adding reactant means it needs to shift to the right to address that stress, and if we add product, then it's going to need to shift to the left to address that stress. We can look at this in terms of Q as well, right? Adding reactant means that Q is going to be too low, right? We're increasing the denominator of this expression, which means that Q is going to drop below K, and again, we're going to see a need to shift to the right, too many reactants. If we add product, this means Q is going to be too high, and we're going to need to shift to the left. And this is a really important qualitative thing to know about equilibrium reactions, just the fact that if we apply a stress to a system that is at equilibrium, it will respond in a certain way, and this we call in chemistry Le Chatelier's principle. So if we want to remove reactant and product, this will apply as well, right? If we remove product, that means that there's too much reactant, and therefore it's going to need to shift to the right. Right? If we remove reactant, it's going to need to shift to the left because there's not enough reactant there. So how we change the system will cause the equilibrium to change its balance and is very important. You might think, well, how are we going to remove chemical from a system? Oftentimes it's by introducing another reactant that's going to react with either the products or reactants of this one. And so as that secondary reaction goes, it may draw out one of the species that's involved in the equilibrium we're studying, and therefore it's very important to understand what's going to happen to our entire chemical environment. All right, so I hope you enjoyed the video. Definitely take a look at the quiz, and I look forward to talking to you in the next one.